Okay, so let's finish up chapter 20 about magnetic fields. And let's just start with a reminder of our first right-hand rule. And one thing you always have to remember is use that right hand. Step 1, point your fingers in the direction of the velocity or the current. If you have more than one moving particle, if it's moving through a conductor, then it's going to be a current instead of just a velocity. You may have to rotate your hand, but get your hand where your fingers are pointing in the direction of the velocity of the current, and you're able to rotate your fingers toward the magnetic field. If you can do that, your thumb will point in the direction of force on a positive charge or a conventional current. If you need to know the direction of force on a negative charge, it will always just be in the opposite direction. So for example, if I have a magnetic field and it happens to point to the left, and I have a current, we'll go ahead and it happens to point at this direction. I'm going to put my fingers of my right hand pointing along this current, and they'll need to rotate towards B. So they'll have to rotate this direction. That tells me that in this case, the force is out of the page for a positive charge or current. It's into the page for a negative charge. Let's just do one more. Let's say instead, let's suppose that we have a current that is directed straight into the board. So if we have current into the board or into the screen, your right hand, you need your fingers pointing straight into the screen. They still have to be able to rotate towards the left. In this case, the force will be straight up on a positive charge. So our force vector, if I want to make it red, would be going straight up. Fingers into the board, rotate towards B. Make sure you realize those green lines are B. And our force will be straight up. I want to do that because we're about to learn our second right-hand rule. And it really helps if you feel really good about the first right-hand rule first. The second one's actually easier. So let's move on. This is section 20.7, and it talks about the magnetic field for a long, straight conductor. Obviously, this conductor has to have current going through it. So a piece of wire with a current going through it. If you have a piece of wire like this, let's do it a little different than my notes. Let's say the current's going this way. What you have to be able to do is you grab it with your right hand with your thumb in the direction of the current. So I would need my thumb to point this way, and I would grab it with my right hand. Notice my fingers are going to curl around There's my hand. I can clean that up a little in there. Ooh, there we go. And I grab it. My fingers will curl in the direction of the magnetic field. So in this case, the magnetic field, it forms those closed concentric circles. My fingers are curling this way, so my magnetic field lines are this way. Now, as I move out farther, there's still a magnetic field, but it makes sense that the magnetic field as you get farther away is going to be weaker. How much weaker? Well, this brings us to our first new equation, a formula that's going to give us the magnetic field strength. So here's our rule for getting it. Let's write our direction rule first. Second right-hand rule. We'll actually get a third rule, but not until the next chapter. So only 2 right-hand rules in this chapter. Step 1, point thumb, and this is the thumb of your right hand with current. You're basically just grabbing the wire, fingers curl in the direction of B. So we can tell that that's the correct direction. The other direction would be this way, and that would be the wrong direction in this example. So your fingers tell you what the correct direction is. The size of the magnetic field, this formula is a gift. We don't have the calculus. We are not familiar with the laws we would need to try to develop it. It says simply that it is mu naught, that's a constant, times the current divided by 2 pi r. B, of course, is your magnetic field strength. And we, of course, are going to measure that in Tesla. This constant is a constant known as vacuum permeability. It's one of my favorite constants, only in that it has a very exact value. It's exactly 4 pi times 10 to the negative 7, and it's measured in Tesla meters per amp. So crazy units like lots of our constants. I, of course, is current. And R is the distance from the center of the wire. And if you look at the formula, obviously as R gets larger, you're farther and farther away from that wire. The strength of that magnetic field is going to decline. Like all of our formulas, I have this on the formula chart. It's not something you will have to be able to remember. Let's do a quick example. Suppose we have a power line. It's carrying a current of 100 amps. And it wants to know at what distance from the line is its magnetic field equal to Earth's magnetic field. Now, the magnetic field for Earth is equal to 5 times 10 to the negative 5 Tesla. So we take our formula, and we would like to solve it for the distance. So if I rearrange that, I get that R is equal to mu naught I over 2 pi B. and I simply fill in all the blanks. 4 pi times 10 to the negative 7 times 100. 2 pi times 5 times 10 to the negative 5th. If I want to, I can do some canceling. 4 pi divided by 2 pi is actually just going to be 2. 2 times 100, I can do this without a calculator. 2 times 100 gives me 200 times 10 to the negative 7. This is what we did before we had calculators. 5 times 10 to the negative 5th. 200 divided by 5 is 40. 10 to the negative 7 divided by 10 to the negative 5 is 10 to the negative 2. It's going to be in meters. So our answer to 2 significant digits is either 40 centimeters, that would be 40 centimeters, 10 to the negative 2. So 40 centimeters or 0.40 meters, that gives us our 2 sig figs. So about 40 centimeters from this power line, the magnetic field due to the power line is very close to the magnetic field due to the Earth. Okay, our next section, section 20.8, talks about the force between two parallel wires. If I have a wire here, call this wire wire 1, and it's got current flowing through it, I'm going to call that I. And I have a second wire, it's got another current, we're going to call that I prime. They're parallel. They're separated if we go center to center by some distance r. We want to find out, let's think about the force on wire 1 due to wire 2. Now we know that Newton's third law says that force is going to be the same on both wires. If wire 1 exerts a force on wire 2, then wire 2 exerts an equal force on wire 1. We know that the force is going to be equal to IL times B2. B2 is the magnetic field due to wire 2. Normally we say the force on a current carrying wire is just ILB, but we know that B2 from the formula that we just got is mu naught I prime over 2 pi r. That gives us the force exerted at this particular point. So my force is IL mu naught I prime over 2 pi r. So we normally would write it this way. Mu naught, I'm going to change this. Let's go ahead and divide by the L. So we get F over L equals mu naught I prime over 2 pi r. F over L is the force per unit length. Obviously, so that would be in newtons per meter. Everything else we've already defined. The one thing we haven't talked about yet is the direction. F is attractive. If I and I prime are in the same direction. F is repulsive if I and I prime are in opposite directions. Now this formula applies strictly to parallel wires. We're not going to talk about other orientations, but truthfully, if they're not parallel, if they're perpendicular, they would not even have a force. One other thing I want to talk about is let's look at what the magnetic fields look like. Suppose that we have two wires and the current's into the board. So there's two parallel wires. They're both directed into the board. They're separated by this distance r. What do the magnetic fields look like? Well, picture your thumb pointing into the screen. We're going to grab that wire. You can see that the magnetic field lines form concentric circles like this. This one does the same thing. If we get right at the midpoint, right here, this magnetic field is pointing straight up, and this magnetic field, which goes the other way, would be pointing straight down. So, if they're in the same point, same direction, you can see that at the midpoint, that magnetic field is actually equal to 0. Notice when they point in the same direction, these lines will actually eventually join and you'll get kind of magnetic field lines that look like this as they go around. Now, if they point in opposite directions, let's think about what happens. If this one points into the board and this one is coming out of the board, so I have two wires. Notice the magnetic field lines, let's look at right at the end point, for this wire are going to go this way when you do that right-hand rule. So that right here, the magnetic field actually points straight down. And the magnetic field for this one on the left, they're actually clockwise. So it would point this way. It would also point down. So at that particular location, the magnetic fields would actually add together. So if this distance is, the midpoint is what, 1/2 r? The magnetic fields would add together. So we know B is equal to mu0 I over 2 pi r. And we're making the assumption that these are equal currents. If they're not equal currents, then these will not cancel out to be 0. They won't have the same strength. I should have made that clear earlier. If the current is the same and they point in the same direction, then at that midpoint, they'll cancel out. Now, if one of them has a larger current than the other, it will not be 0 at the midpoint. The larger one would dominate. If they have equal currents and they point in opposite directions, then basically you have this situation. Our distance, let's do it for the first one over here on the left, that's going to be mu0 I over 2 pi r over 2. And this one is going to be mu0 I prime, which is the same as I, 2 pi r over 2. Again, since those are the same, we could actually add this. This is mu0 I over pi r. plus mu naught I over pi r, which is going to be 2 mu naught I over pi r. R is this distance between the two. All right. Main thing I want you to know is when they point in the same direction, that is an attractive force. When they point in opposite directions, that is a repulsive force. Now, there are a variety of other types of conductor configurations. The most important of these involve current loops and solenoids. So let's move on to the last section that we're going to cover. There's a couple more in chapter 20, but we're not covering them. Current loops and solenoids. So, current loop, we picture a piece of wire bent into a circle. We're going to let current go in the loop, and then current will come back out of the loop. If you grab it with your hand, and you have your thumb pointing with the current, you can see on the outside, you're going to be going into the screen, and on the inside, you'll be coming out. So we do the dots and X's. We get something like this. Now notice that's where the loops would be. The X's on the outside are much farther apart than the dots on the inside. In fact, we often want to know what's the strength of the magnetic field right at the center. You can picture magnetic field lines of force coming out through the center. We can see that. So at the center of the loop, and again, this is just pretty much a gift because we don't have the calculus we need to develop these. The magnetic field strength is mu naught I over 2 r, and r is the radius of the loop. It's not the distance from the loop. It's the radius of the loop, and this formula tells us how strong the magnetic field is at the center. Now, truthfully, almost more often, we do not have a single loop. We often have a situation where we have a coil. And a coil is made out of lots and lots and lots of loops. In this case, the magnetic field at the center is just N times mu naught I over 2 r. N is equal to the number of loops, or they're often called turns. It's how many times you wrap that wire around something. So, for example, suppose we have a situation where we have 200 loops or 200 turns. The radius is 12 centimeters. And the question says, find the current necessary to produce a magnetic field of 5 times 10 to the negative 3 Tesla. That's about 100 times stronger than Earth's magnetic field. So if we take our formula, B equals N mu naught I over 2R, and we solve it for I, we get I equals 2RB over N mu naught, and we just fill in the blanks. 12 centimeters is 0.12 meters. We just have to always remember to go back to our SI units. N is 200, and mu naught is 4 pi times 10 to the negative 7. One thing I want to point out is the number of loops is generally considered to be an exact quantity, so it never affects your significant digits. Something that you can physically count, and you can count how many times you wrap that coil around, can be considered exact. And all we do is punch that in a calculator and we get 4.8 amps. Now, a solenoid is basically a long coil. Think like a slinky, although it doesn't need to be that long. You basically have a situation where you have loops. They're usually very closely spaced together, but you have a long coil of wire. Its magnetic field at the center. And you say, why at the center? Well, one of the interesting things about a solenoid is if you have current flowing through it, it actually has a magnetic field right through the middle like a bar magnet. You think of the North Pole coming out and the South Pole going in, but of course it wraps around, forms those closed loops, but right at the center, coming out at the ends on either side, is the strongest point. So, what's the magnetic field at the center of a solenoid? It's mu naught lowercase n times the current. Pretty simple formula. N is equal to the number of turns per meter. We'll probably work one of those when we go over this in class together. And then our final one we want to look at is the magnetic field. Magnetic field of a toroid. A toroid is basically a donut-shaped solenoid. Take that and turn it in a circle. A lot of times when they make solenoids or toroids, they actually wrap them around a metal core, like a soft iron core. So if you think of having a ring of metal like iron, and then you go and you wrap around and around and around. Although probably most of the time these wrappings would be so close they'd be touching. It's just hard to draw. So that's a solenoid. It looks rather like a donut. Now, remember when we said they like that magnetic field lines, they like to form closed loops. They also like to travel through magnetic materials. The result is the magnetic field lines stay pretty much exclusively inside this loop. Whether there's an iron core there or not, even if it's just air inside the loop, the magnetic field lines look like this. The strength of that magnetic field is mu naught Ni over 2 pi r. Now, r is measured from the center of the circle. So if you think of this inner radius being r1 and the outer radius being r2, the value of this r has to be between r1 and r2. The magnetic field will equal 0 outside the toroid. So if you're not in that range, the magnetic field is 0. B is confined to the interior, the inside I'll tell you what, let me go ahead and get a textbook and let's just work one example with either a solenoid or a toroid or both. Let's see if we can find one. Chapter 20, here I am. Let's look at 68, just because it's the only one I see that's a toroid, and it's our last formula up here. So this is problem 68 in your textbook. It says a toroidal solenoid has inner radius R1 equal 15 centimeters and an outer radius R2, which is equal to 18 centimeters. The solenoid has 250 turns, so that's our value for N, and carries a current of 8.50 amps. So our current through this is 8.50 amps. What is the magnitude of the magnetic field of the following distances from the center of the torus? So we want to find it at R equals 12 centimeters. We want to find it at R equals 16 centimeters. And at R equals 20 centimeters. Well, two of those are super easy. If you are less than 15 centimeters in here, B will equal 0. If you are greater than 18 centimeters, which is 20 centimeters, that B will also equal 0. The 16 centimeters is within the interior of the toroid, so we can actually calculate at 16 centimeters. It will be mu naught times, well, I'll tell you what, let's go ahead and fill in our numbers because the formula is right up there above us. It'll be 4 pi times 10 to the negative 7. N is 250. I is 8.50. Over 2 pi R, and R is 0.160 meters. I want to point out that the measurements that matter have 3 sig figs. The current has 3 sig figs, the radius has 3 sig figs, 250 turns is exact. Mu naught, the 4 pi times 10 to the negative 7, is also exact. This 2 pi in the formula, also exact. So I just need to put this in a calculator and see what I get. I'm probably going to go ahead and cancel 2 pi over 4 pi is just 2. So let's see. I have 2 times 10 to the negative 7 times 250 times 8.5 divided by 0.160. And my magnetic field came out to be 2.66 times 10 to the negative 3 Tesla. I went ahead and put it in scientific notation. I rounded it to my 3 significant digits. It's a reasonable looking magnetic field, so I feel good about that answer. All right, that finishes up chapter 20. I will see you guys in class.